Hello, hello, hello. Well, today we'll start where we left from, but before that, let's see something interesting. Like we made Wi-Fi RF, and I just uploaded that on GitHub on my repo. So you can follow this link along and well, forget if you want to just get inspired from this and start writing code. This was our Wi-Fi RF motion sensing. This is some system architecture I made using AI, nano nano. And these were our screenshots, as you might have remembered from somewhere in this video. Well, the part 14. All right. Yeah. So this is our GitHub repo now. And we have distributed into two POCs, like proof of concepts. One was where before using Rust for everything. Second one, which is POC2, we are using Rust for loops also. And the Python is just for sake of interactivity. It's not doing anything. It's not running loops. It's not doing anything. It's just giving it a call to get a function from this library, which is Rust engine and all that. And that's how it's working. If you want to see, well, just go into POC and let's go into Python and see test engine. Test engine was giving us only RSI. So we are not now calling RSI. We are not, getting RSI again and again. We are just using a function called RF engine, which is, our Rust engine. And we are saying get RSI, which is a py function defined in a Rust in lib.rs, which is library. And we are passing our device name or interface's name, which is vol0. And that's how we are getting RSSI. We are not running loop in here to get RSSI. We are running just single loop so that we can print RSSI every time we fetch one. All right, so that's what's happening right now. So this is one like very short Python code, which is just for the sake of interactivity. And the second one is test is done run engine. So this will just run engine, which is start engine, and it'll start giving us motion, variance, and energies values. The screenshot might have been there. Oh, yeah. Where are the values? Oh, I might not have uploaded those screenshots, but I will upload it soon enough. But there's some mention of it, no? Yeah, like this motion, energy, and variance from run engine. That's the output we get. If well, I want to send some sort of screenshot of it, I will do that. But for now, yeah, this is it. So our, Wi-Fi RF took well much of our time for the past few days. So let's get back from where we started from, like where we left from. We left it at static on this topic, which was a lifetime in 15th module. So 15.4 lifetimes, and we left it static, and we have to cover up traits also. So let's get into it. All right. So this was our static. So let's read it. Rust has few reserved lifetimes names, though one of those is this static ampersand static. You might encounter it in two situations, like someone like this ampersand a static string, which is reference of static string, and then we are assigning it a value of hello world, a reference with static lifetime. All right. So this is a reference because of ampersand and with a lifetime of static because of this static keyword. Another way to find out static is, static as a part of trait bound. So we are writing a generic trait over here of type T, and X is taken as a value of T, which is a generic trait, where T is now, instead of having a lifetime of A or anything like that, it is having a static lifetime. That's it. And then we are defining some generic trait in these curly brackets. All right. So both are related but subtly different. And this is a common source for confusion when learning Rust. Here are some examples for each situations. So we have a reference lifetime, which is some sort of situational example. As a reference lifetime, which is, ampersand static, indicates that the data pointed to the reference lives for the remaining lifetime of the running program. It can still be coerced to a shorter lifetime. There are two common ways to make a variable with static lifetime, and both are stored in the read-only memory of the binary. Now make a constant with a static declaration, and then make a string literal which has a type of reference of lifetime of static. Reference of, like, with a lifetime of static. Now it's giving us following example for display of each method. So we have first of all static lifetime, and we are making a constant out of it. So constants are obviously static, but yeah, we are making it. We are declaring static, and then num, which is our variable constant. Well, constant is just a placeholder which is holding the value 18, not a variable, let's say, because variable can vary. So this is a constant variable, if I can say, but variables always vary. Ah, we'll say this is just a constant, no variable, right? Which is of type either, and it is also static, so it will be compiled into as a binary, into the program as a binary. So yeah, this makes sense. Now the comment says that returns a reference to the num where it's static. Now the lifetime is coerced to that of the input argument. Now we have a function coerce which takes the lifetime of a, and then we have, well, nothing, or the wildcard, which has a reference with a lifetime of a and of type I32, and then it is giving out a result of the same type. And what we are doing actually is nothing. Just whatever the number is, we are coercing that into the static number or the reference of static number, which will become sort of 18. Now function main. Let's static string. So I am in read only memory. All right. So we are making a string literal. This is our string literal. Static string is the variable. I am in read only memory is the, well, memory, sorry, the thing that's getting into memory. What shall we say? It's a string. All right. Now we are printing the static string by declaring we are printing the static string, and then we are printing the value over here. That's it. And it says when the static string goes out of scope, the reference can no longer be used. The reference to the static string can no longer be used, but the data remains in the binary because it is a, well, string literal, which we can say like it is a static string. All right. So can no longer be used, but the data remains in the binary. So we are causing a static which has a lifetime of the programs to become, well, unusable after going out of scope. But it is there in binary. But rules doesn't allow us to use it freely. That's what it does. Now we have another scope with another example. It says make an integer to use for coerce static. So we have a lifetime num, which is 9. And then we are causing, we are saying coerce static, and we are using coerce function, which was over here. And then we are passing our value to it, which is 9. And then instead of getting 9, we are getting a value of 18, isn't it? Yeah, because it's coercing the value to 18. Any value given in will come out as 18. That's it. So 18 gets stored over here. And then we try to print the coerce static. We'll print, well, the 18. And then we are saying num stays accessible. So num, which was declared over here, stays accessible. The rest of them, well, they go out of the bound. So Let's try running it. See, num stays accessible. Core static is 18, not 9, because it was coerced into 18. And then static string, which is I am read-only memory, printed over here. All right, so let's move on. Since static reference only needs to be valid for a remainder of the program's life, they can be created while the program is executed. Just to demonstrate, the below example uses the box leak, all right, to dynamically create a static reference. In that case, it doesn't live for the entire duration, but only for the leaking point onwards. So this is our well method in box, which is called leak. Let's see what it does. It takes the lifetime as a generic, and then well, it takes box which has two T and A generic type. They are not generic type because it is not defined. Ah, it is. So A is with a lifetime of A generic, and then we are saying that the result value or the return value will be a reference of lifetime A mutable T. So what it does is consumes and leak the box. So it consumes first of all whatever comes in and then leaks it. So it returning a mutable reference which is ampersand mutable T. All right. Oh. Now that type T must outlive the chosen lifetime A. If the type has only static reference or none at all, then this may be chosen to be a static. Okay. So this had a lifetime of A, but since it's leaking now, so it has to well outlive the chosen lifetime A, and this may be chosen to be a static or well something like that, but it has to now outlive the lifetime of A. This function is mainly useful for the data that lives for the remainder of the program's life. Dropping the returned reference will cause a memory leak. If this is not acceptable, the reference should first be wrapped with box and from raw function, producing a box, and this box can then be dropped, which will properly destroy T and release the allocated memory. Note, this is an associated function, which means that you have to call it like box leak and call it on B instead of B dot leak like this. This is so that there is no conflict with a method of inner type. Now we are seeing some examples. We are calling box leak on X, which is box new 41. And then we are saying static reference, whatever it is, just plus one. Dereferencing it first of all using star. And then we are trying to make it 42. And we are asserting the equivalence whether it's 42 or not. Well, it should be. Let's close this program. Let's get back to our program. So this is done. This is done. We were at box leak. So this will be our next program that we'll learn to dynamically create. So over here, just to demonstrate, the below example uses box leak to dynamically create a static reference. So it does not create static reference by itself, but it becomes static reference because we are leaking the box. In that case, it definitely doesn't live for entire duration, but only for the leaking point onwards. Yeah, because before that it had a lifetime of let's say A or something like that, but after that it has to live like a static for the entire duration. Uh, in that case, it doesn't live for the entire duration, but only for the leaking point onwards. Let's see the code now. We have external create rand, and then we are saying use rand and fill. Uh, from rand library, we are taking fill, and then we are saying creating a function called random vector, which will return a static type, and u size will be oh. So this is an array. We are first of all taking a reference and we are making that reference static. And then in an array, we have a u size, which is, The type of things that will be stored in this array will be of type usize, and because it's not defined well, unsized number, something like that. This is usize. And the numbers of elements in this array will be 100. So there will be 100 numbers with a type of usize. So those 100 numbers will be of type usize. Then we are saying inside that function, in random vector function, we are saying that let mutable rng is equals to rand and thread rng. What does that mean? I don't know. And then we are saying let mutable boxed, which is box new. And then we are creating a new pointer for another vector, which is, has a 100 zeros in it. Yeah. But that array is also a pointer that is getting stored into a boxed. All right. Because box always stores a pointer towards something that is boxing. And then we are saying box dot try fill. We are trying to fill what? Mutable RNG. Oh, so we are a mutable RNG and we are trying to fill it with some values. And then we are saying unwrap it. Like there is any error, just exit it from here. Or else, if there's nothing, move on. So then we have a box leak and we are leaking the boxed. This one is getting leaked now. So it had a reference of A, let's say. This was a lifetime of A. It had a reference of A because of RNG, mutable RNG. Now, does not have that. It does not have that. So from here onwards, it'll start leaking. So it will become static dynamically. Like it was not static earlier, but now it became static. So the return value will be in static. So that's why we were saying that we'll get a static and, well, a pointer towards an array, and the array will be of 100 elements, and those 100 elements will be of type usize. So this was our random vector function. Then we had a main function which is like let first and let second, and then both of them are static or are of type static, usize 100, which means it is of return value of this. And we are using random vector to get the return value from these random vector functions. And then we are storing that and we are saying assert any, like they are not equals to each other, first and second. If they are, well, we should get some errors. So it's before that we are getting some sort of error that thread RNG in crate rand is not found. Why? I did not do anything. So it's telling us to first of all use something like this or just say something like this thread RNG. Then we have another which is try fill. No method named try fill found in structure which is box. It says use something like this. So it's trying to help us. I don't know, this is what we want to use because we are just learning for this the first time. Let's use a AI. Yeah, we can edit this code, so we will try. At least trying error. Thus, well, it says use something like this. So it just gave us a new, well, code. Well, key changes were this just use thread RNG and fill directly without just importing the whole crate and then over here it says same thing, but it will also create some problem. Let's see what it does. Let's first of all clean everything, paste new code, try running it. So these were, yeah, I thought. So there is no thread RNG in the root. Use randfill. Well, we did, and it says that unused import, something like this. So we imported it, but we are not using it. But we were trying to use try fill, and now we can't. See? How about we make it default and just change whatever this error tells us to? Let's make it default. Is it? Yeah, it is default now. Let's only change what this error tells us to. So first it says there is no thread RNG, not found in RND brand. So where is this thread RNG? Over here. All right. What shall we do? So it says instead, I think this is RAND and then version 0.92. And then from there, we are calling thread RNG explicitly and saying use that. And then instead of using thread rand and then thread RNG, we can directly use thread RNG. All right, let's do that first of all. Use the latest version, which I think 0.9.2 is. Let's copy this. Let's come up over here, paste it. Instead of rand, well, let's, yeah. Paste it so that we get a reference of what's happening. We don't have to, undo it again and again. So this was the change it was telling us to make. And the next thing it says is use randfill, well, unused import of randfill. So we are importing it and we are not using it. So what? They should just give us a warning. Oh, so it is a warning. It is not an error. All right, we'll do those. Then it says no method name try fill found for this structure. So it says instead of, try fill, we should use boxed fill. Let's do that. So instead of this, it is telling me to use this. Now if I try running it, it still doesn't run. It says, well, this is a warning, this is a warning, this is a warning, but this is an error. Oh, so it has been renamed. So thread RNG has been renamed to RNG. So why hasn't this doc changed from there? Mismatched types. I don't know what's happening. And it is out of my sort of expertise. Like I've never faced this issue ever before. And I can just go with the suggestions it is telling me to. And that's what I uncommented, and now it's telling me to add it. Well, just suggesting me, not telling me, but yeah. And instead of thread RNG, what if we just use RNG? Because it says thread RNG has been deprecated. And RNG is not found in the scope. What we can do is instead of thread RNG, we can over here also say RNG. Is this good? It is good. Now we are not getting much of a warning except for this one. It says we are importing rand fill, but we are not using it. What about now? Now the warning is gone. Now the last two errors. Well, it is telling me to remove this try fill, just give it a fill, but that also shows some error. So what can I do? It's telling me to do this and then run it. But now we get another sort of error that this fill method was expecting integers, isn't it? Expected integers and found a mutable thread RNG. So what? Like this is a problem, but give me something that can expect this thread RNG. And there's nothing like that. It says unwrap method not found in. Well, no method named unwrap found for unit type in the current scope. So first of all, let's not call this because it is also causing error. And then second of all, try doing something with the fill. It says there is a, well, let's say a method defined which is taking a mutable self and value of t. And again, it is expecting an integer but found mutable. This gives us an error which we can't resolve. So how about not even using this, just use this and we say use rand fill, that's it. Now it's suggesting me to use this, but then not working at all. And because try fill is not using something from rand fill, it is being flagged as unused imports. What can we do over here? Should we use GPT? Let's see. Well, it hangs too much, so that's our issue. Over here, let's say why this program doesn't work. Let's give it a program. And the second thing I want to try is there any difference if we just use it in our own place? Like, is 13.rs? Let's create something like 14.rs. All right, 14.rs. Let's paste it. Let's try running it. If we get the same error, well, this is not a problem for playground. Yeah, we get the same error. First of all, it says, yeah. So instead of just extern and this, it says just use like something like this. No RNG, no nothing. The whole crate. And then it says the same thing. Instead of try fill, use fill. First of all, let's make this change. Extern create rand and with a version. Extern create rand and with a version. It says something like 0, 9, and 2. Exactly, and it says don't use this, so we'll just GCC it. And now, yeah. So it says now can't find the crate. But it was suggesting just a minute ago. Something like this. Wasn't it? Like I don't see much of a difference between this and this. But now it says can't find. And over here it was trying to help us. Like you might be missing a crate named. Add it to your project and import it in your code. And then second thing is again, fill and try fill. So this is an issue. So your program has several issues related to incomplete imports, API usage, and crate naming in the RAN ecosystem. So I'll go through the exact problem and then show the corrected version. So incorrect crate is something like RAN 092. This line is invalid. So if we try using it, this is invalid, but our playground was not giving us any error for this. It was sort of suggesting us to do this. Now, crates are imported by their name, not their version. If you installed 0.9.2 in cargo.toml, oh, you stim. So first of all, you can't do something like this because you have to create a cargo.toml. And for that, well, you have to create a cargo new project. And we are not doing in that. So let's just remove this 14.rs, right? And then it says, or typically use, so yeah, it sort of figured out all these problems. You wrote this fill, but fill trait lives in RNG or RNG core. RNG functions, something like this. Try versus fill. If this works finally, well, we'll see the output. If it doesn't, we'll move on. That's what we should do now. Cleaner, non-leaking version. Well, we want a leaking version, no? We want a leaking version. That's what we wanted to see. Thread RNG not found. It again says do this. Let's see the non-leaky version. Will it make any difference? Yeah, instead of u size, we are saying zero u size. Is that much of a difference? Will it work? If it doesn't, we move on. Yeah, it doesn't. It still says not found in RAND and all that. Well, I don't know the library RAND, first of all. Second of all, to use the cargo's functionality, we have to create a cargo new and that will take a time. We are not going to do this for this corrupted sort of function. But we know it can leak, all right? Theoretically, it can leak. We can make box leak work because that's what it does. This function or this method in box leak does the same thing. Like, all right. So let's move on to our trade bound. Let's just remove this program. I don't like seeing so incomplete program. Then just me. Now trade bound. So mm, so as a trade bound, it means the type does not contain any non-static reference. Like the receiver can hold on to the top for as long as they want, and it will never become invalid until they drop it. So it is important to understand this means uh, that any owned data always passes a static lifetime bound, but a reference to that owned data generally does not. So now we have a library called standard formatting debug that we have used multiple times to sort of implement our own, format or are just flags that would debug. That says create a function that is printed and it takes the input, and then we are saying implement debug for that and plus static lifetime, and then we are saying print a static value and whatever the input over here is, which is of type implementation. We are implementing debug plus static. I don't know what it does, but it seems nice. And then in main, we have a I, which is equal to 5. So I is own and contains no reference. Thus, it's a static. And then we have a print 8I. So we are passing that I, which is 5, into this. It should print a static value passed in is 5. And then instead of directly passing I second time, we are passing a reference of I. So oops. Is it oops oops or object oriented oops wala oops? I think it's oops wala oops. And the reference of I only has the lifetime defined by the scope of main, so it is not static. What does it say? Borrow value does not live long enough. Why? It should. Let's see now. Yeah, it prints this. And if we do this, it will not print it the second time. So let's do it before this. How about this now? What's now? So let's uncomment this so that we don't see any error because of. Huh. Now you see the original error. It says binding I declared over here, and then print on line 9. And then on line 10, we are saying print and we are taking the reference of I, which is, borrowed value does not live long enough. Why? Because it has to go out of this main function to the printed function. And we are taking a reference of it, but it does not live long enough to be taken as a reference. So argument requires that I is borrowed for static. I is dropped at line 15 before going to the printed. So I is dropped here while still borrowed. So that is a problem. What's next is function printed, which is, implementing debug plus static. Let's not do that. Let's do this. And lastly, just read this comment and then we'll say compile error. It says, oops, ampersand I has lifetime defined by the scope of main. Exactly. So in main, I is defined because I is defined in main, so it has a lifetime comparable to main. So it is not static, obviously, but over here it says or expects a type, I guess, static. So this gives us the same error, like not gives us, but shows us the same error that we should get. And it says, yeah, ampersand I borrowed value does not live long enough because it lives only in the main. We cannot pass it as a reference to print it. All right. An argument requires that I is borrowed for the static, which but I is dropped at line 15 for us. It says for line 16. Yeah, because we moved it. Then we have the final topic, which is elision. Elision, isn't it? Yeah, final topic elision in 15.4 lifetimes. So some lifetime, oh, it is very short. So some lifetime patterns are overwhelmingly common, and so the borrow checkers will allow you to omit them to save typing and to improve the readability. This is known as elision. Elision exists in Rust solely because these patterns are common. Now the following code shows a few examples of elision. For more comprehensive description of elision, see the lifetime elision in book. So this is Rust by example. This is not Rust's book. So it says see the book. We'll see that, sir. And this blows around. Well, yeah. What was this? This was a leaking box that we took it from a book. And what it should do, or what we are expecting it to do, first of all, it has a pointer towards 41, and then it's taking that X, the pointer in a box leak, and we are trying to leak that. And it is, since it's mutable, we are also trying to dereference it to the value like 41 and then add 1 to it, so it becomes 42. And then we are trying to equate whether our static reference became 42 or not. And then it says drop say unsafe box from raw, and then we are passing the static reference because it is a leaking box. Let's try running it. So it says compiling finished, and since we got no errors, it means this was actually 42. So this became 42. So if we just use println, which is a macro, and we try printing the value of static ref, we should get a 42, isn't it? Ah, it was expecting a semicolon, obviously. Yeah, it gives us a value of 42. If we said instead add 9 to it, we would get an error over here that is not equal to 42, and over here, exactly. So it says left became 50 because we added 9 to 41, and right was equating to 42. So this is not equal. If we say NE, which is, negative of whatever the EQ is, so it will give us no error because that's what we are expecting now, that both of them are not equal, and we are getting a value of static reference. So it works. Obviously it does, but yeah, we've seen it working now with our own hands. Over here, we had a lifetime of elision in a Rust programming language, which is, the Rust book. Which topic, which one, which one, which one? In generic types, validating reference with lifetimes. Over here, lifetime elision. Great. I think we must also go through this Rust programming language book, but later on. First, let's finish this elision. So our code, we have a elided input function, which takes x, which is a reference of i32 instead of just i32. And then we are saying println, and we are saying elided input, and we are printing the value of x, whatever the x we are passing to this elided input. So the comment says elided input and the annotated input, which is this one, essentially have identical signatures because the lifetime of elided input is inferred by the compiler. Oh, all right. And this annotated input is of type, well, generic A with a lifetime of A. And the X is using that lifetime A for the reference of I32. And then we are printing that X. But for elided input and annotated input, it says essentially have identical signatures because the lifetime of elided input is inferred by the compiler. So it also sort of becomes like this. And since this is also a generic A, it is also inferred by compiler. So they both have an identical signature. Now, similarly, it says elided pass and annotated pass have identical signatures because the lifetime is added implicitly to elided pass. So elided pass has implicitly, like we are not explicitly defining it, it is implicit that it is taking a reference of I32 and the lifetime should be something towards A. And annotated pass, we are saying, well, explicitly that it should have a lifetime of A. And again, a reference of I32 with a lifetime of A. That's it. So they both will become identical because this implicitly means that it has a lifetime of ampersand A. Ampersand no, apostrophe A. What's this? Yeah, it exactly means this one. All right. So that's what it's telling us. But that was implicitly. If we did something like this, it will become explicit. All right. Then we have a main. So it's telling us just use shorthand instead of just defining, the lifetime and all. Our compiler is smart enough to understand that. That's what it's telling us. I think so. Then we have a main. We have a x is equals to 3. We are passing the reference of 3 or the x into elided input. Good. Over here, we should, well, be able to print it. We are passing the same value, which is x is equals to 3 to annotated input. It should also be able to print it. And then we are printing these elided pass and annotated pass over here, right? Because it takes the x and returns the x. So nothing interesting. So let's see what it is. Oh, so elided input is 3, annotated input is 3, elided pass is again, well, 3 because it returns x. That's what we are printing. And annotated pass is 3. So it just says instead of explicitly, defining the lifetime, we can let it remain implicit and it'll work fine. No issues at all. Elision. Let's read elision again. So some lifetime parameters are overwhelmingly common, and so the borrow checkers will allow you to omit them to save typing. That's it. And to improve the readability. Yeah. So that's elision. Now this is known as elision. Elision exists in Rust solely because of these patterns are very common. So let's finish this. And this is our new topic, traits. Then it has 9 subtopics. So including this, we have 10 topics. So let's start. Traits. So a trait is a collection of method defined by an unknown type, which is self. It says they can access other methods declaring the same trait. So they can access other methods declared in the same trait. Trait can be implemented for any data type. So in the example below, we define animal, which is a group of methods, and the animal trait is implemented for the sheep, which is a data type, not a trait, allowing the use of method animals with a sheep. Let's see, we have a trait animals, we have a structure sheep, which has a value of naked, which is, Boolean, whether true or false, and then a name for that sheep. That's it. That's the structure sheep. Then we have a trait animal, which says associated function signature self refers to the implementer type. We have a new, which is taking, well, a new animal, and we are giving it a name, and we are returning the self. Then we have a name, which is taking a reference of self, and then returning the name or the static string, reference of static string. And then we have a noise sort of method, which takes the self or the reference of self and returns a static string, whether it has a noise like moo or something like that. I don't know. Sheep has a noise of what? I don't know. Let's see. Cow does the moo. Sheep is bah. Right. But why is naked? Like bah, bah, what is this? With a question mark with a exclamation. I think we have to see this. So the trait, well, we have a name, we have a noise, same name, but different. And then we have a talk. So we have a trait can provide default method definition. So we have a talk method which takes the reference of self, and then it tries printing the self name and self noise. Okay. So if we say talk, it does this. Let's say the name is Dolly and says whatever the noise is. Okay. Makes sense actually. And then we have an implementation for the sheep, which is, a function saying is naked. All right, give me 2 minutes. Give me 2 minutes. All right. So we have an implementation for the sheep, which is, method whether it's naked, and we are taking the self, we are taking the boolean, the self dot naked. If it is true, we are returning the boolean, which is true. If it is false, we are returning a boolean, which is false. Then we have implementation for shear, which is, if it's time to, well, take out the wool from the sheep. So it checks whether the self is naked. If it is, well, it is already naked. And else, like, we need to share it or gets a haircut. So whatever the name is, gets a haircut if it is not naked. And then after the haircut, it becomes true, like it gets naked. So yeah, self naked dot true. What if it got sort of half naked? Then we cannot make it false. Otherwise, we cannot give it a haircut another time. Like let's say we were sharing a sheep and then we left it in between. Like, yeah, we left it in between and got busy with another sheep. Now this sheep is half shared, like half haircut is done, the half is well left, but we just made naked is equals to true. That's the issue. But let's not make it complicated. We are just getting an example. Now implement the animal traits for the sheep. We are implementing the animals for sheep, which is, the sheep, which is the implementation for the structure sheep. And then we have a trait animal, and we are combining both of them. We say that we have an implementation for animal, and we are implementing that for a sheep. So animal had a name, noise, and talk. And we can also define a new animal by using new method. All right, so for implementation for the sheeps, we are saying new. So this will have a new method which will, you know, can define a new sheep with a name and whether it has hair on its body or not, so naked or not, so false or true. Then we can have a name, or we'll just print the name, whatever we defined over here. So it just returns the name when we call the function name or method name in this implementation. And then when we call for the noise, well, it gives us a noise. So if it is a naked, like it has no hair, it says bam with a question mark, like what have you done? Else, well, it is enjoying. So that's what the noise is. Good. Now, when we say talk method for implementation of sheep, so these were like general implementation over here. Over here for animal, this was general trait. Like we can implement that for a cow, we can implement that for a cat, we can implement for anything. Like is naked won't make much of a sense over here. Uh, all right, but name and noise will. So that's why this is a general trait. Whereas for sheep, is naked makes sense. Like it has a hair on its backs, or it does not have, and the shear also makes sense. Like we can share a sheep, we cannot share a cow or cat. Doesn't make much of sense. And then we are combining both of them together over here uh, with a noise, and is naked was well a method in implementation of sheep, and this noise well was an implementation or sort of function in the trait animals. Yeah, noise. And we are combining both of them together over here. So we create a noise, like we say noise, then it checks whether it's naked, then it gives us this noise, else it gives us this noise. Then we have a talk. For example, we can add some quiet contemplations, like it pauses briefly and whatever, let's say Dolly pauses briefly and then we see the noise, whether bang or bang, whatever, with a question mark or exclamation mark. Then in a function, well, main function, we are creating a sheep first of all, and we are naming that variable as Dolly, and the sheep animal new, like Dolly over here. We are not giving it a value of naked, true or false. Try removing the type annotation. We will. Like it says, try removing this type annotation. Isn't it? Now we say dolly talk, dolly share, dolly talk. That's it. So if first of all it says bah, which is not naked, enjoyment, and then it says bah, like it is naked now. So Dolly pauses briefly and then it says, where? Like the implementation over here, not over here. This one. We are not calling this talk, says, and all that. We are getting pauses briefly. Right. Why? Because this is a sheep and we already have an implementation of sheep. So this will not go looking for an animal. It will just go to the sheep. So that's why this type annotation was important. So Dolly dog, it talks. We give it a haircut. So it says Dolly gets a haircut over here for the shear or the sheep. The shear method in the implementation of sheep. And then we say talk again and it changes its tone. And it says, well, try removing this annotation, type annotation, which is, defining the type of dolly. We'll get an error or something like that. It just timed out. So we get an error saying that dolly.talk type must be known at this point. So it's talking about this. Whereas for this, type annotation needed. So it says type annotation is needed. You cannot just remove that. So we'll give it a type annotation and everything just works. Yeah, it says help. Consider giving Dolly an explicit type, which is it is a sheep. How about we do something else? So let's create another structure and we'll call it a cat. All right. And we'll not create a implementation just for the cat. And naked, well, it doesn't make much of a sense. We'll just give it cat a name, from the animal. It'll have a name, it'll have a noise. We'll implement cat for or animals for cat, and then it will talk. So that's what our cat will do. So let's take this statement and just make it work. We want to see what happens for cat. Yeah, cat, and then it has a name. Uh, no naked values, so no need for this. Then name, and then not this. We just say cat. And then cell.name is used. Noise. So is naked or not? I don't know. I don't care. We'll just make it meow. Simple. MEOW. Let's see whether it was. Yeah. So we cannot just make it meow like this. We have to code it. Then we have to say meow. MEOW. That's it. This is a return value from noise. And when we are saying, well, talk, it first of all gives its name like cat. What should be named cat? Like, give me a name of cat. Oh shit. I don't know. I've never named a cat. Let's get a cat name. So, cat names. And for the rest, let's try defining it. So, we have implementation animal for cat. And then over here, we can say after Dolly, we can make the implementation for the cat. It's not a sheep, so it's a cat. The name is not Dolly. The name is Primate. Something like that. Well, imagine Primate being a cat. No idea. Cat names. Luna. Let's take Luna for example. All right. So we have a variable called Luna, and then give it a name called Luna, and we say cat talk. All right. Cat and talk. That's it. Will we get any errors? Well, I was expecting you, so don't worry. Cannot find the value cat in this scope. Cat talk not found in this scope. Why not? Why not? Why not? Why not? Why not? Why not? Like we have implemented for cats, then we have everything, but we have not. We don't have any implementation for the cats. But we don't need any because it's not naked, it's not sharing. So what is the issue? I don't get it. It says cat not found. Dolly. Oh shit. We cannot do this. We have to do Luna. Luna and talk. Yeah. Now Luna pauses briefly and says meow. That's it. And if we want implementation for the cat, like the sheep does, like over here, mm, we can take another thing. Like now we'll modify the cat. All right. We'll modify the type cat. Instead of name, like yeah, name will be there, but uh, compared to sheep, it will have a instead of naked, it will be neutered, right? Neutered, and this will be a value boolean, which is true or false. Like cat has been neutered or not. I don't care about the spelling. Let's take it. Copy this. All right. Traits for animals, for sheeps. Mm-hmm. Do implementation for the sheeps. We don't want it. Let's remove one. Make that. Oh shit. And instead of is naked, we have a is neutered. Isn't it? And we are passing the self. We have a boolean. We see if it's boolean or not. And then for sharing, for neutering. All right. Let's make it is neutered. All right. This seems much more appropriate. So this is neutered, but we are taking is neutered, and we are taking the self. Instead of checking self dot naked, we check self dot new, not mu, but neutered. All right. If it is neutered, it is good. It returns the value true or false. If it is not neutered, let's neuter it. So we'll make a function called neuter ring. Just make it neuter. All right. We check is neutered instead of is naked. Eutered is neutered. Spelling mistake, neutered. Now this is good. We print if it is already. So B is already neutered. Let's just paste what we have. It's already neutered. Uh, gets a haircut. Well, gets something cut, but not here. And a long silence along with that. And over here, self dot neutered was there, right? And we'll make it true. So it has been neutered. Now for the implementation of cat, we have to, well, make it sound difficult, like if and else. All right. For now, it's just meow. We'll change it very soon. Like if self, oh, not delf, but self dot is uh, neutered. If this gives us true value, we'll say, well, it is an angry cat because it has been neutered. So, oh, we can write question mark. So let's avoid it. Else, we'll make it a happy cat. All right. But cat is never happy. So we still make it some sort of happy. All right. This seems right. Now, let's check it. Cat is missing a neuter. Oh, we were defining cat somewhere. Yeah, over here. That's why I copied that, neutered bool. Now it should run. Ah, another problem. Neutered bool, not a value. Well, it is true or false, no? So, naked, false. All right, so we are defining naked, which is, but over here neutered, it is not neutered, so we'll say false. FAL, not flares, but false. Now, no problem. Yeah, well, it's not neutered, so it's very happy. Let's neuter it. So, we'll say Luna, and then we had a function, or we had a method, which was for neutering it, neutering the cat. Implementation new, names, noise, talk, nothing like that. But for sheeps, no, we can't find it. Is neutered. And then if it is not, we can say neuter. So we'll just say dot neuter, not neuter, and it will, well, neuter the cat. So now it will not print much of anything because it does not. But it is now neutered. So Luna gets something cut. Well, it does. And then Luna talks back. Now what? Now it's a sad meow. Well, yeah, it is. So I think I love this program because the first thing I learned in, C was something related to meowing one times, two times, three times. Like I learned looping through this. So yeah, let's create a 14.s. And now we are in Rust. We have a sheep and a Luna, Lolly and a Lula. They are both talking. So it's an impressive thing. All right. So this is done. We are done with the traits. We have defined traits. We have implemented both the structures. We have implemented traits for the structures, and we can move on now. I think so. We are next to a derive. So compiler is capable of providing basic implementations for some traits via this derive flag or attribute. Now these traits can still be manually implemented if more complex behavior is required. The following is a list of derivable traits. So we have a comparison trait, which is EQ, partial EQ, ordinals or odd. I think it's ordinals, but what is ordinals? I don't know. Odd and then partial odd. So these are comparison traits. EQ, partial EQ, odd, partial odd. All right, so four. We have a clone to create T from ampersand T via a copy, but it copies every bit of it, and it mostly applies for you know pointers and all pointers, structures, strings, all these things. We use clone for numbers. It automatically gets copied, or we can just copy it. Then we have another copy to give a type copy semantic instead of move semantic. We have done that earlier, so we know how we can just define a structure which can be copied, and when we just use it without taking a reference, it copies it or clones that structure. Now we have a hash. So to compute a hash from a reference of T, so yeah, if we have a reference of T, we can hash that. I think, like, I know a hash, but is it the same hash that I'm thinking about? Hash, hasher, hash slice. I think it is. It will be hashed differently from A and BC conjoined together. So it's the same hash that I was thinking about. So let's get back. So this can be also, computes a hash from a reference of T, and it can be used as a attribute. I just say it like a flag. Like, is this hash a flag or it's an attribute? I don't know the technical terms yet, but I think it is attribute. Is that what it says? Oh, rest by examples, attributes. We've read attributes earlier. Yeah, we've seen attributes like these, derive, debugs, and attribute a value. So it is called attribute. Well, not a flag, but attribute. Then hash, after hash, we have a default that does to create an empty instance of a data type. So if we have any data type and we have defined a default, we can just create an empty instance of that data type. We have debug, which is used to print with this formatter, which is a debug formatter, where we don't implement the print for that structure. We can use a debug to just print that structure. So now we have a code, and well, we have attribute derive. We say partial EQ and partial odd. I don't know what this partial odd does, but partial EQ is something related to equivalence or something like that because of EQ, like attribute EQ. Nee, assert EQ. We've used assert EQ. So I'm assuming from there, partial EQ is something very similar. Now, centimeter, a tuple structure that can be compared. All right, so centimeters is a tuple containing F64, and it can be compared. That's what it says. So partial EQ and partial odd. Because of these attributes, it can be now be compared centimeters. And then inches, a tuple structure that can be printed. So inches is a structure that can be printed using debug because attribute debug is defined for this. And then we are implementing for inches, a function that is called 2 centimeters. So if we give it an inch, the self, which has a value of inch, it converts that into a centimeter. So it takes the reference of inch, inch that is passed into it, and is equals to self. So from self, we are destructuring the inch. First of all, we are getting the inch, and then we are saying inch as F64. We are converting the I32 to F64, and then we are multiplying it with a decimal, which is a float point value, which is a conversion like 1 centimeter. No, no. 1 inch has 2.54 centimeters. So now we are multiplying this 2.54 with inches, and we are getting the value of centimeters. And that's what we are returning because there is no semicolon over here. All right. So if we just use this method, which is 2 centimeters on inches, it will convert the inches to centimeters. That's what it does. Now we have a seconds, which is a tuple structure with no additional attributes because we don't see any hash and attributes derived over here. So yeah, it is just seconds of type I32. So seconds are in I32. Now we have a main function where we are implementing all of these. So let's see. So we first of all say 1 second is equals to second, and we are passing 1 to it. Now error seconds can't be printed. It does not implement, this debug formatter, which is, derived debug. So it cannot be printed using this formatter, and it cannot be normally printed because we have not implemented the normal print for that. So we cannot print 1 second for that matter. Now it says, uncomment this and see the error. We know it will give us error, so we'll see that later. Then second error is that seconds can't be compared. It doesn't implement the partial EQ trait. So partial EQ is a trait which helps us to compare. So over here also we have a partial EQ. That's why it said something like tuple structure can be compared. But what about partial OR? We shall see that too. So it says, it's trying to compare 1 second with 1 second, and this is true. So if this was true, it must return, Boolean like true. But since we don't have a flag, or sorry, attribute that says we can implement the trait partial EQ, so we cannot compare it. So we'll not get a value true from here. So this will also give us a error. That's what it says. And we'll uncomment and see that. But before that, let's just read this program and see a normal output. Then we have foot, where we are saying in a foot we have 12 inches. That's what we are saying over here. And we want to convert that in centimeters, I guess, somewhere, foot to centimeters. But before that, we say foot equals to, and then we are printing the foot, which is inches. And we have derived debug, so we can print it easily using this. So we'll see inches is 12. All right. And then we are defining meter, which is for centimeter, 100 centimeters equals to 1 meter. And then what we are doing is we are saying let CMP, which is compare. So we are comparing if foot to centimeter, foot, and we are converting that foot to centimeter using this function, this method. And then we are comparing whether it's less than the meter. If it is, we say smaller, else it is bigger. This is, 12 inches, which is how many foots? Well, 1 foot, and we have to then multiply it by 2.54, which will make it, let's open up Python, but it should make something like 2.54 multiplied with 12, isn't it? 24.6, 24 plus 6, so 30.4. Exactly. So this will give us a 30.4, which is in centimeters, like 30 centimeters, 30.4 centimeters is obviously smaller than meters. So we'll get a smaller. Else we can get a bigger, like if it's not 12, instead if it is 24, then it will become something like 60.8. And if we make it instead of 12, 24, we make it 48. Now it's bigger. So we'll change the value and we'll see the output also. But over here it says 1 foot is this, the value of, bigger or smaller than 1 meter. So 1 foot is smaller than 1 meter, obviously. So 1 foot equals 12 inches because we are printing it over here. And then we are saying print whether it's smaller or bigger. So now let's not make it 1 foot, right? Let's make it 2 foot. Can we do this? Implicitly or explicitly multiply it in inches. Yeah, now it's 24 and then it's still smaller. How about we make it 3 foot? Now 3 foot is still smaller. Exactly. Now 4 foot would be larger or bigger. So 4 foot, which is 48 inches. If we do the math, which is 30 multiplied by 4. So this is, and let's do multiply 4 and 121. If it was just 3, yeah, it was 91, so it was less by 9, approx 9. All right, 8.6, something like that. Yeah. So we now know this is our normal input, or sorry, normal output, and now we shall see some errors. Errors, errors, errors. Why? Why will be seeing some errors? Because we have not derived the flag for that, or the attribute. Sorry. I'll take some time to remember this is called attribute, not a flag. So we have to derive some attributes. Then we'll be able to print it using debug mode. So first of all, let's see the errors. So first of all, don't see two errors simultaneously, just see one error at a time and solve it. So it says, yeah, required formatter and all that. So it has not implemented derive debug. So it says derive debug. So this is our attribute. So derive debug, use this attribute, and we are good to go. And as soon as we define it over here, we can print it and it works. See, it works. We are able to print our seconds, but we still can't, compare it because it has no partial EQ defined as an attribute. So yeah, we see that we cannot equate it. It is trying to help us with no removing the brackets, but brackets are not the errors. So yeah, we know that now. So now it says, use this flag. So we will use a partial EQ and to, define two attributes together, we just use a comma in between. And what was the use of partial odd? I still don't get it. But let's see. Partial EQ will allow us to equate. Let this is true, so we are not getting any errors. And if it is, we might be able to print it. So if we just print the Boolean value of this is and true. Exactly. So we might be able to print this, which will be a true. True. Exactly. So no problem now because we have introduced partial EQ and debug attributes to this structure seconds. Now, what else is remaining is this partial odd. Like if if by any chance I remove this, will this cause any sort of error or will it not? And if it does, I want to see the errors. Suddenly it gives us an error saying this is true, unnecessary parenthesis around. Oh, this is a warning. And it is helping us by saying, remove this parentheses. And because of partial odd, when we remove partial odd, we are getting something like put 2 centimeters. We cannot compare it to meters, which are, both centimeters. That says binary operation uh, less than cannot be applied to the type centimeters. Why not? Because we have not. Oh, the partial odd gives us the permission to sort of use these binary operations to compare. Now that's great. All right. So it says note an implementation of partial odd might be missing from the centimeters. That's why we said partial odd. All right. Now I get it. Now I get it. So let's, you know, create partial odd. Let's do again. And now it uses this binary operation. It does the binary operation. It compares both of these and we are good to go. So what I was taking for granted was actually because of this attribute, partial odd. I thought it should just work because they both are the numbers, but I forgot something that they are both defined by us. So they should not act like a normal numbers. They are our structures that we have defined. So we have also, need to define that we can compare it using partial odd or, the binary structures like less than equal to something like that. But again, why this works? Like 1 second is another structure that does not have this partial odd, but it has partial EQ. So because of partial EQ, we can use, equating functions. But since this does not have a, less than equal to because of partial odd, so we cannot do this. What it says, now it will give us an error of partial odd. See, it gives us a partial odd error. And if we just define a partial odd over here, we can do this and it will give us a false, first of all. If we do this, we'll get a false. Give us a false, gives a false. So it gives us a false. And now let's try removing partial EQ because we don't want to see the equating. Oh, let's remove the comma. Now without partial EQ, partial odd doesn't make much of a sense. So no implementation for seconds equal to seconds. And we are not even equating it. So this was just assuming that since there is no equal to, why are we even comparing it? So it says use this partial EQ. All right, so we know it. We know it now. So let's undo our changes and let's move on. Where's the change happening? Yeah, over here. Partial EQ. Let's move on now with a false because we are not equating it like EQ equals to. We are saying less than. So 1 second can never be less than another 1 second. So they both are. Let's move on, I guess, from derive to returning traits with dyne or dynamic. Well, now we have another implementation for animals, and instead of sheep, like instead of cat, we now have a cow, which has a noise of boom. Sheep has a noise of ba, and animal is the trait defining the function noise. We don't have any neuter, we don't have any naked or all that. We just have a noise. No name, no nothing. Structure sheep is defined. Well, is just there. Structure cow is just there. We have trait animals exactly. We have implementation for animals for sheeps, and noise is bear. And for cow we have moo, and they both are static string because yeah, exactly. Moo and ba is looking like a static string. Then we have a random animal. We are saying random is sort of a number, F64, and we are creating a pointer for dynamic animals. And then we are saying if random number is less than 0.5, then we say create a sheep. And if it is not, just create a cow. So that's how we are creating cows and sheep. Good. So random number is 0.24. So it will create a sheep. So animal is equals to random animal. That will be a sheep for now because of this condition. So print your randomly chosen animal and it says, well, it says bye because it is a sheep. So let's see. Yeah, it says bye because it's a sheep. If we just make it, well, 2.24, 2.234, whatever. Now this is a sheep. So instead of creating generic traits, we created a dynamic one, which will have a, fat pointers, which will have a, lookup tables and all that to see whether what we are doing. And we are just passing the same thing like sheep and cow all together over here. And we choose animals dynamically. We don't define we have a sheep. We don't define we have a cow. We can use a runtime, to get this value, get this random value, and we can at runtime like get whether this animal is sheep or cow, and we can do this again and again. So that's why that's what dynamic trait is better at from generic trait. uh, why is it important? Because we can call it dynamically. That's why it is important. Is it heavier than generic trait? Obviously it is, but both of them have their pros and cons. What is it? What from I can remember is dynamic trait has fat pointers, so it has a lookup table and all that, and the pointer is very heavy. So yeah, it takes a lot of memory space. Whereas a generic trait, what it does is for all the implementation, like we had an implementation of sheep and cow. Remember that? No, earlier in generic trait, we had an implementation of sheep and we made a cat. All right. So instead of just taking both of these animals as just one, we had two implementation for those both of these animals, even for the noise making and all that. That was like binary heavy. So if we have multiple generic traits, it will make the binary heavy. And instead, if we have a dynamic and one trait, now the both animal like sheep and cow will be over here only. We don't need a multiple implementation of both of them. We can just define it from here. We can use it from here, and we are good to go. So it's a runtime factor. So let's see what it says. Returning trait with dynamic, not generic, but dynamic. So Rust compiler needs to know how much space every function returns type requires. This means all your function have to return a concrete type, unlike other languages. If you have a trait like animal, you cannot write a function that returns animal because its different implementation would need different amounts of memories. Sometimes it's bear, sometimes it's moo, different amounts of memories. However, there is an easy workaround. Instead of returning a trait object directly, our function returns a box, which is a, well, pointer, all right, which contains some animals. And a box is just a reference to some memory in the heap, which is there. Allocated animal. So heap allocated animal. All right. And we can return a trait from our function. We can return a trait from our function. Rust tries to be as explicit as possible whenever it allocates memory on the heap. So if your function returns a pointer to trait on heap in this way, you need to write the return type with a dynamic keyword, which is box type dynamic. What was the generic? Just taking that as a lifetime of a and all that, taking this a reference and all that. So that was generic trait, taking t, whereas this one is dynamic. So I think we are good to go. Let's move on from there. And dynamic type is something that I like because we can just decide at a runtime. First of all, it is well slower compared to the static time. Why? Why? Like you can ask why. It's not. It is because the static type or the generic trait always are defined as a binary. So binary is always faster than data lookup and fat pointers, pointing towards each other's data. So you have to dereference those pointers to get to the value. Whereas in generic trait, it is already there in the binary. So that's why generic trait is faster, dynamic trait is slower than that, but not very much. But if you need, calculations, matrix multiplication, you should use what? Static, not dynamic. All right. Static generic trait. Let's move on. Operator overloading. This is our third subtopic, I guess. Exactly. So I think we cannot finish this whole traits, but all right, we are doing it and we have 10 to 12 minutes. So let's see this operator overloading and we'll finish it. Uh, in Rust, many of the operators can be overloaded via traits, and that is operators can be used to accomplish different tasks based on their input arguments. Now, this is possible because operators are syntactic sugar for method calling. For example, the plus operator in a plus b calls the add method, as in a dot add b. Now, this add method is a part of add trait, and hence, the plus operator can be used by any implementer of the add trait. A list of the traits such as add that overloads the operator can be found as core operations. So let's see what this core operation is. And let's remove this hash one, standard hash, core operator. So do we see any so standard ops, and we are getting add and subtract from there. And to add, we just, where are we adding? Where are we adding? I guess we are using plus and we are using minus, but we can just, in brackets, we can say dot add and dot subtract. All right, let's get back to it. Hence, the plus operator can be used by any implementer add traits. A list of the traits such as add that overloads the operator can be found in core ops. And over here, we are just taking the standard ops, and we have a structure foo, we have a structure bar, we have a derived debug for structure foo bar, another structure foo bar, and we have a derived debug for that. We have a derived debug for bar foo because we'll be printing it using question marks. Then we have an implementation of ops add. From here, we are taking add, and for the bar, for the generic bar, uh, we are taking the add and we are implementing it for foo. We say the type output is foo bar, obviously, and then we are adding the RHS self, taking the self, and then we have a RHS which is bar, pass through add inside add, and then it makes it foo bar. So foo is there, and we are adding a bar to it using add bar. So it says print foo dot add bar was called like this exactly, and we get a foo bar as a result. So type output is foo bar. So the standard operation add trait is used to specify the functionality of the plus. Here we make a add bar, the trait for addition with RHS of type bar. The following block implements the operation foo plus bar is equals to foo bar. Exactly. Now we have another operations add for bar, which is like type output will be bar foo that we have defined as a structure over here. Then we are saying creating a method for that add, and we are now have a RHS of foo instead of bar, and we are adding foo to the bar, so it will become bar foo. So all right, exactly the same implementation. We are printing bar dot add foo was called, and we are returning the value bar foo. So yeah, this will be returned and we can easily print it. So first of all, we have print foo plus bar. It will add foo plus bar. So it was like foo is not a number, bar is not a number, and there is no implementation of uh, two non-numbers combining together. Like we cannot add a plus b. All right. So to do that, we just made two structures, and we implemented the add operation for that, and now they are just getting concatenated like in Python. We concatenate two strings, but these are not just strings, they are structures in itself. All right, so let's see. We should get foo bar and then bar foo. So foo dot add bar was called, so it gave us foo bar, and then bar dot add foo was called, so it gave us bar foo, exactly as we expected. Is there any problem? I don't think so. There is much of a problem. So let's move on. Now, since drop is well lengthy one, so we'll just leave it together for tomorrow or day after one. Right. So from drop, we have iterators, implementation traits, clone, super traits, and ambiguating overlapping traits. All right. And then we'll go to macro rules. So we have to start from 6.4.